In this video, I'll cover hypothesis testing for two means when we have independent samples. So what does it mean to have an independent sample? First, we'll define independent and dependent. Independent samples are samples that are selected from two or more populations in such a way that the values in one sample do not impact the probability of the values in the other sample. Where in dependent samples, or paired samples, samples that are selected in a way intentionally to match the values in the second sample to those in the first sample. This is done for the purpose of controlling for extraneous factors, controlling for things that aren't important in our study. So let's work through an example. Suppose a professional job placement firm that monitors salaries in professional fields is interested in determining if the fluctuation in prices of oil and the outsourcing of computer-related jobs have had an effect on the starting salaries of chemical and electrical engineering graduates. Specifically, the job placement firm would like to know if the 2015 average starting salary for chemical engineering majors is higher than the 2015 average starting salary for electrical engineering majors. To conduct this test, the job placement firm has selected a random sample of 124 electrical engineering majors and 110 chemical engineering majors who graduated and received jobs in 2015. Each graduate was asked to report his or her starting salary. So to start with, I've run descriptive statistics on our two columns of data. We're interested in the average starting salary for chemical and electrical engineers. So you can see the mean starting salary for chemical engineers in this data set was $64,167, and for electrical engineers was $61,392. Using these samples, I want to talk about first what the point estimate of the difference is between the average starting salaries for chemical engineering majors and the average starting salary for electrical engineering majors. The point estimate for the difference is really just the difference between our sample averages. So we're trying to estimate the difference between chemical engineers and electrical engineers' average salaries, the true value, but we don't know that, so we're going to use this sample average for each of those two and calculate the difference. This is really just to say how far apart on the number line are chemical engineers and electrical engineers' starting salaries. So the point estimate for the difference is the difference between the averages in the two salaries. So chemical engineers made $64,167 and a penny on average, where electrical engineers made $61,392 and 93 cents. We take big number minus little number, and we get the point estimate for the difference. In other words, it looks like on average it's $2,774.08 between these two samples. Now this number is not zero, so we might think chemical engineers and electrical engineers do make different salaries. However, this could just be sampling error. So to know more, we need to drill into this deeper. One way we can do that is to create and interpret a 90% confidence interval for the average difference between the engineers. The confidence interval is calculated by taking the point estimate, as always, plus or minus the critical value times the relevant standard error. So our point estimate is the difference between the two sample means. The critical value, that would be a t or z-score, and the relevant standard error. We're going to use Minitab to do this because there are a number of formulas, and instead of trying to apply a bunch of different formulas by hand, we're going to let the computer do the work for us. One of the things we need to know before we go over to the software, though, is whether we can assume that the two samples have equal variances or not. So back to our spreadsheet here, we see the standard deviation of chemical engineers and electrical engineers. We're going to use the rule of 2 to 1. The rule of 2 to 1 says that as long as the standard deviation for one is no more than 2 times the other standard deviation, we can assume equal variances. So in this case, chemical engineers have a standard deviation that's about 25% higher than electrical engineers. Only 25%, not twice as high. So we can assume equal variances for the case of our example. To calculate our confidence interval in Minitab, we're going to go to Stat, Basic Statistics, two sample T. We have two samples that we're attempting to compare to each other, but those samples are independent. When you have independent samples, you want to pick two sample T. There's nothing about column 1 that connects to column 2. Those are not the same people or the same region. We just have two groups of engineers. Once you click on two sample T, you will have several options in the drop-down box. So the first option says both samples are in one column. We would choose that if we had numbers in one column and the other column was an ID. So we had the dollar figure in one column and we had chemical engineer or electrical engineer in the other column. That's not the case for our data. In our data, we have chemical engineers in one column and electrical engineers in the other column. For that, then, we would select each sample is in its own column. We could also have summarized data. For summarized data, we would have the average, standard deviation, and sample size for each of the two columns of data. So we're going to pick each sample as in its own column. When you do that, you'll have to bump in then your two samples of data. I always put these in the order that I want them to match up with the subtraction. So when I had that point estimate, I had chemical engineers minus electrical engineers. I'm going to then put in chemical engineer first and electrical engineer second. For the confidence interval also, we need to click on this options box here. Make sure that our confidence level is correct, and for our case, we're allowed to check assume equal variances. So I just noticed that I didn't change to 90% as I should have in that calculation, but we'll go ahead and run with the 95% confidence interval. Our output here generates for us the confidence interval estimate. You might notice also that here is that point estimate for the difference. This is already our X bar for chemical engineers minus the X bar for electrical engineers. If we calculate a confidence interval, we should be able to interpret it. So to interpret this confidence interval, we would say we are 95% confident that chemical engineers make between $1,437 and $4,111 more than electrical engineers. So from this data, it sounds like chemical engineers make more than electrical engineers. We can also conduct a hypothesis test. So conduct a hypothesis test to determine whether the 2015 average starting salaries for chemical engineering majors is higher than the 2015 average starting salary for electrical engineering majors. What that means is that our alternative hypothesis is that the average value for chemical engineers is greater than the average value for electrical engineers. That's what we're trying to prove. So our null hypothesis will be that the average for chemical engineers is no better than the average for electrical engineers. Now, to be able to put this on a graph, we have to convert this. Our alternative hypothesis is that when we take the average for chemical engineers and subtract out the average for electrical engineers, we will have a positive value. Chemical engineers make more than electrical engineers. So if I take chemical engineers and subtract out electrical engineers, I should get a positive value. I'm looking for some difference between the two that's statistically far above 0. That means our null hypothesis is that chemical engineers minus electrical engineers will be no different from 0 or maybe even less than 0. So when we work hypothesis tests, we should always start with a graph. I've got my normal distribution here. My center of this distribution now is 0. I'm assuming that the true difference between chemical engineers and electrical engineers is 0. What I'm trying to do now is use my sample data to prove that the difference that we got, our sample difference, is statistically far away from 0. Something up in our upper tail, far away from 0. We'll go back to Minitab to do this calculation. Stat, basic statistics, to sample T. So the same place that we calculated the confidence interval can also perform the hypothesis test for us. We've already punched in chemical engineer and electrical engineer into our dialog box. But now in our to sample T options box, we're going to make sure in our alternative hypothesis that we match that up with the alternative hypothesis we had on the previous slide. We're trying to prove that the true difference between the two means is something statistically greater than 0, the hypothesized difference. If you had something other than 0, which we hardly ever do, you would change this box right here. So hit OK again, and we get our output. For those of you that like to use the t-value, you get a t-value here. This looks pretty high. We would need to go to our t-table or our t.inv function to get the appropriate t-critical value. I'm going to use the p-value approach because, as we talked about before, that's the easiest method for doing the comparison here. So what we've got on our graph here is that difference, our $2,774, has approximately 0% chance of happening if the two average starting salaries are equal to each other. Since the p-value is less than alpha, our alpha being 5%, we can reject the null hypothesis. We can say that chemical engineers start out making significantly more than electrical engineers. That's all for now. I'll see you again soon.